Alright, so let's begin. Hello everyone, I am Sri Shubhadar. I am a PhD student associated with the Center for Systems and Control at IIT Bombay, and I'm also the TA for this course, WE46 Linear Dynamical Systems. So welcome to fifth week's tutorial session. So we'll start by writing down the topics that are going to be discussed in today's session. First one is going to be the controllable canonical form. How to obtain the transformation which transforms a state space LTI system to the CCF form. Controllable, canonical. Have how to design the gain matrix K. So design of K such that A minus BK has eigenvalues at desired locations. That is pole placement or eigenvalue sign. And then finally, we'll see how to design the feed forward gain or tracking. Alright, so let's begin with the first topic. So we'll start with a question and we'll learn how to derive the controllable canonical form as we go along. Alright, so this is the first question. Find the similarity transformation. Transforms the following pair into CCF. A and B matrices are 6, 4, 1, minus 4, minus 5, minus 4, 0, 0, minus 3, minus 1, and B is 1, 0, 0. Alright, so let's first check if the pair AB is controllable. So for n equals 3, the controllability matrix is going to be BAB A squared B. Alright, so let's compute this first. So the controllability matrix is going to be used in computing the similarity transformation T. So I'm going to say that T is the similarity transformation. Alright, so AB is so you can check the computations. This is just the first column. A squared B is A times AB, which is 6, 4, 1, minus 5, minus 4, 0, times 6 minus 5, 0. This is 36 minus 20, minus 30 plus 20, and then 15. So this is simply 16 minus 10, 15. Alright, so the controllability matrix is 1 0 0, 6 minus 5 0, 16 minus 10 15. Now this is a square matrix, so we can just determine the determinant to comment on the rank. So this is simply minus 5 into 50, which is non-zero. Therefore, the pair AB is controllable. Now we'll talk about the CCF form first, okay? Okay. So we have a general LTI system. X dot equals AX plus B. We want to transform this into a system such that YC plus BCU, and we want to find this transformation such that AC and BC have some nice forms. So I will write down what AC should look like. So AC looks like 0, 1, 0 sort draw, 0, 0, and then 1. So 1 is shifting to the right after every row, and this goes on. We have the last row. So last row looks like some constants alpha 1, alpha 2 up to alpha n. Both A and AC are of size n by n, and BC looks like 0 zeros and 1 at the end. Okay, so what's so special about this form? So, for example, this is y dot. So let's see. Y1 dot is simply y2. Y2 dot is simply y3. So on. Yn minus 1 dot is yn. And yn dot is summation alpha I yi plus u. So this implies that we have a chain of integrators. And the input is present only in the last state. Alright, so this is known as the CCF form. So now we want to find a transformation matrix T such that we get the state Y. Alright, so there are a few steps. So let's see. Let's say that the first state is some matrix C times X. So note that C is not the output matrix here. Alright. If this is the case, then y1 dot, which is y2, is simply cx dot. And now we can substitute c to find out that this is ax plus bu plus cax plus bu. cbu. Alright. So we want cbu to be 0 because y1 dot should be something like exactly y2, right? And we can write y2 as ca times x. Now if you find out what y2 dot is, then this is simply ca times x dot, which is ax plus bu. This is ca square plus cabu. And now we want cab to be 0 or ab to be 0. And let's say for third order system, we are till y2 dot. So what we want is c applied to b, ab, a square b, and so on should be 0. This is still an minus 1 is 2 equals 0. So now you can see that this is uh, looks like the controllability matrix. Of the controllability matrix C. So this is script C. All right. So there are two conditions then. The first one is that yk is CAK minus 1x, where k ranges from 1 to till n. And the second one is that CA to the power k minus 1b should be 0. So that we can have the chain of integrators. And this is also true for 1 to up to n. Okay. So if this is the case, then what's the transformation matrix? So let's see. We have y1 equals cx, y2 equals ca square x, and so on. So the transformation matrix is c ca square all up to ca to the power n minus 1. Okay. So now the objective is to find the matrix C using the controllability matrix script C. Alright. So let's say that C is alpha 1, alpha 2, alpha 3. These are some scalars. So let's first check the dimension of C if this is correct. Yeah. So C is going to be, for example, from this we have uh, this is just a scalar. This is C times n by 1. This is going to be 1 by n. So for n equals 3, we have alpha 1, alpha 2, alpha 3. And now we have to find out these constants. So we know that C times B should be 0, or the C times the first column of the controllability matrix should be 0. This implies we have alpha 1, alpha 2, alpha 3 times the first column of the controllability matrix. That is 1, 0, 0. There should be 0, which simply implies that alpha 1 should be 0. Similarly, we have C times second column equals 0, which implies that 2 x minus 5, 0 should be 0, which implies that alpha 2 is 0. Now, since n is 3, we have that C applied to the controllability third column of controllability matrix should be a non-zero constant. Let's pick it to be 1. So again, we have alpha, let's just put these values 0, 0, alpha 3 applied to, uh, let's check, minus 16 minus 10, 15. 16 minus 10, 15. This should be equal to 1. Which implies that alpha 3 is 1 over 15. Alright, so now we know the row C, which is 0, 0, and 1 by 15. So then in this case, what's the transformation matrix? It is C, CA, and CA square. So now you can compute this. I'm going to write down the transformation matrix directly. So let me just see. Yeah, this is 0, 0, 1 by 15 as it is. Then we have c times a, which is minus 1 over 5, 1 over 15. Then we have 1, 1 and 1 over 15. Alright. So now we need the controllable canonical form. So we need AC and BC. So how can they be computed using the transformation matrix T and A? So we have y dot equals ACY plus BCU, and we have x dot equals AX plus BU, and the transformation y equals TX. Alright, so y dot is simply TX dot, which is T A times T inverse Y plus BU. This is T inverse Y plus TBU, and you can see that this is AC and BC. Okay, so we also need T inverse. I'm going to write down the matrix directly. You can check this later. T inverse is 4, 5, 1, minus 5, minus 3, 0, 15, 0, 0. And now you can simply substitute in AC. Okay, so AC is, just a second. AC becomes 0, 1, 0. Then 1 is shifted to the right, and the last row is going to be minus 19, 6, and 1. Similarly, BC is transformed to 0, 0, 1. So you can see that exactly is this chain of integrators after here, and some non-zero coefficients in the last row. We have the CCF form. Let's wait for a few seconds. I think the screen has not synced yet. Just a second. Let me try this. Alright, so you have the CCF form. So now we'll use this uh, after maybe the second or the third question to find out the gain matrix K so that we can place the eigenvalues at the desired locations. But let's first start with the simple example. Alright, so we have the second question now. So consider the LTI system. X dot equals AX plus BU. A is the 2 by 2 square matrix 0, 1, minus 1, minus 2, and B is 0, 1. So we have three parts of this question. The first one is the system controllable? Then the second part is compute a matrix. Such that the eigenvalues of A plus BF are both zeros. And then C, find the matrix. For the matrix. Okay. The closed loop system. X dot equals A plus BF, X stable. So the first part is quite easy. Let's just first do this. The controllability matrix is BAB, where AB is just the second column. So we have 1 minus 2. This is 0, 1, 1 minus 2, and the determinant is minus 1. For the pair AB is controllable. Alright. Now we have to find the matrix F such that the eigenvalues of A plus BF are 0. So let's just first find out the dimension of F. This means that this is going to be 2 by 2. E, F, and something which is 2 by B. B is the column, so that's 2 by 1. This is simply going to be 1 by 2. So let's see this. F is, let's say F1 and F2. So this means that A plus BF becomes 1 F2. 0, F1, F2. which we have 0, 0, f1 minus 1, f2 minus 2. Now we want to place the eigenvalues. So let's see. So let's first find out the polynomial of which eigenvalues are 0. Okay, so that is simply s minus 0, s minus 0, which is s square. So this is the desired characteristic polynomial. Characteristic polynomial. And now let's find out the characteristic polynomial for a plus bf. That is simply going to be determinant of a plus bf. Let's see, minus lambda r. Just a second. Say that this is S. So the characteristic polynomial is this is minus S, f2 minus 2 minus S, 1 and f1 minus 1. So this is minus S times f2 minus 2 minus S minus f1 minus 1. This is minus S f2 minus s2s plus s square minus f1 plus 1 equals 0. So let's write this down. S square plus s times this is 2 minus f2 plus 1 minus f1 equals 0. Compare this with s square and we have f2 should be equal to 2 and f1 should be 1. So the matrix F is therefore 1, 2, and then just to verify, you can check that the eigenvalues of A plus BF are 0. Alright, now let's see. So then we have the system A plus BF. So let's write this down. This is part C. BF belongs um, 0, 1, minus 1, minus 2, plus B times F, minus 1, minus 2, plus simply uh, 0. This means that we have debated eigenvalues at 0, which implies that the system is unstable. Was for marginal stability, we need that the eigenvalue at 0 should not be repeated, or the Jordan block should be of size 1 by 1. This implies that the closed loop system is unstable. Now let's look at a similar question. What we've been doing is, I will find out the characteristic equation, find out what the dimension of f should be, assume some constant f1, f2, and then find out their values by comparing the desired eigenvalues and the eigenvalues of or the characteristic polynomial of a plus b. So let's consider another LTI system. S naught equals ax plus bu. A is a square matrix, or 2 by 2 square matrix. So we have to first verify whether the system is controllable. Just 1 second. Verify whether the system is controllable. The second part is all the eigenvalues shifted to the desired location. So let's first find out whether the system is controllable or not. So this is simply DAB. We have minus 2 and then 1 minus 3. So this becomes 1, 1 minus 2 minus 2. This is simply 0, which implies that the pair AB is not controllable. The pair AB is not controllable. Therefore, we cannot shift the eigenvalues to any desired location. So this is because of the theorem. So let's recall the assignment. So it states that only if the n-dimensional system is controllable. So this is the first hypothesis. So the first step is to check whether the system is controllable or not, and then we find out the matrix F or the gain matrix K. So then by the state feedback, is R minus Kx, where R is the reference signal. And real constant vector. The eigenvalues of the closed loop matrix A minus Bk can be arbitrarily assigned. So this is very important. If the pair is controllable, then we can place the eigenvalue at any desired location. So I did that. Complex conjugate eigenvalues are assigned in pairs. So according to this theorem, we cannot place any eigenvalue at the desired locations. Cannot place eigenvalues or all the eigenvalues at the desired location. So this is because the system is not controllable. So determinant of C is non-zero, zero, which implies in this case that the rank of a matrix C is 1. So this implies that only one of the states is controllable. Which implies that we can states can only control or we can only place one of the eigenvalues at that location. Or let's just say only can control only one state. Let's go to the next question. So consider the LTI system. Matrix A as half 1, 1 and 2. 1, 1. So find the feedback or the gene matrix F such that the eigenvalues of A plus BF are minus 1 plus minus j. So we have complex conjugate eigenvalues and they are assigned in pairs. So we'll have to first verify whether the pair AB is controllable or not. So again, this is simple. It's BAB, where AB is half plus 1 and 1 plus 2. This means that C is can observe directly that this is non-zero because this is simply 3 minus 3 by 2. It's controllable. And now we can place the eigenvalues at the desired location. Alright, so we want to place the eigenvalues at minus 1 plus minus j. So the desired characteristic equation becomes plus 1 plus j s plus 1 minus j. This should be equal to 0. So this is simply s square plus s minus sj plus s plus 1 minus j. Yeah, equals 0. This is s square. Please cancel out and so do this. We have plus 2s plus 1 and then plus 1. That characteristic equation is s square plus 2s plus 2 should be equal to 0. Alright. And now we have to find out the characteristic equation for A plus BF. So A is 2 by 2, B is a column vector, and therefore F is going to be a row vector. So let's assume that F is given as some scalars F1 and F2. Characteristic equation of the closed loop system A plus BF. So this can also be A minus BK, the form which we have studied in the week's lecture to lecture slides, but this is also fine. So this is, or you can also find out A minus BK equals minus K. So this is determinant of A plus BF minus SI. This should be equal to 0. So we have, first write down what A plus BF looks like. Half 1, 1, 2 is 1, 1 times F1, F2. Alright, so we have determinant of this f2 plus 2 minus s, and these remain the same. One second. Alright, so now let's compute the determinant. So this is 1 plus half minus s, f2 plus 2 minus s, minus should be equal to 0. So we have f1 f2 plus 2 f1 minus s f1 plus half f2 plus 1 minus s by 2 minus s f2 minus 2s plus s square, and we have minus f1 f2 minus f2 minus f1 minus 1 equals 0. So this goes away, and then we have This is minus f1, f2 minus 2, 2f1 minus f1, which is plus f1, and similarly, f minus half f2. We can compare this with the desired characteristic equation. So let's see, s squared plus 2s plus 2 equals 0. We have a system of two equations in two unknowns, where we have minus f1 minus f2 minus 2 equals 2, which implies that f1 plus f2 equals minus 4, and then we have f1 minus half f2 equals 2, or 2f1 minus f2 equals 4. So that f1 is 0. You can check the calculation. So 0 and f2 is minus 4. Okay. So f is 0 minus 4, and we can verify that the eigenvalues of this BF are located at minus 1 plus minus t. Alright, now let's move on to the next question. Question 4. First question, then second. Alright, so consider a system with a transfer function g hat of s equals s minus 1, s minus 2, s plus 1, s minus 2, and s plus 3. Is it possible to change the transfer function to, let's say, g of s equals 1 upon s plus 3 by state feedback? Is the resulting system stable? Is it asymptotically stable? Alright, so the transfer function, the original transfer function is g hat of s equals s minus 1, s minus 2, and the poles are at this one plus 2 3. So the eigenvalues are from the characteristic equation -1 to 1 -3. Okay. Then we have the desired transfer function with s plus 3 and the eigenvalue here is -3. So we want to shift these eigenvalues to lambda equals -3 by state feedback. What we can do is G hat of S, the numerator remains the same. By eigenvalue assignment, we have S plus 1, S minus 2, S plus 3. Transfer it to 1 upon S plus 3. Is the eigenvalues at S minus 2, S plus. So if I have S minus 1 here, so the cancel and this gets cancelled too. And we have eigenvalues are yeah, this is incorrect, this is not present. So by introducing an eigenvalue at S equals 1, or by placing the eigenvalues at lambda equals 1, -2, and -3, transfer function can be modified to GSF equals S plus 3. And since one of the eigenvalues is positive, this implies that the system is not asymptotically stable. However, the system is Bibo stable system GS equals 1 upon S plus 3 is Weber stable. Because the pole is in the RHS. It's true also. So, at the next question, and we look at a different way of assigning the eigenvalues at the desired location. So consider the LTI system. That equals 0, minus 1, 1, 2 by 3, minus 1, minus 2, 1, 0, minus 3, 1, plus 1, 2, 3, and 0. So first part is to design a full state feedback control law u equals minus kx, which places the eigenvalues or the closed loop poles. So let's say which places the closed loop poles. Ten and the complex conjugate pair minus 10 plus minus 5 or j. And then the second part is if the real parts of the poles minus 100 instead of minus 10, then what would happen to the control rings? We have already looked at one of the methods to find the feedback control law u equals minus kx by equating the desired characteristic equation and the characteristic equation of the closed loop system A minus BK. Now we'll look at another method. So before this, let's just find out what the desired characteristic equation is. This is S plus 10. We have S plus 10 plus 5y. S plus 10 minus 5y equals 0. So you can expand this. I'm going to write this down directly. This is S cube plus 30s square plus 325s plus 1250 equals 0. Okay. So now you can check that the pair AB is controllable. So check or verify that the pair AB is controllable. Find out what the controllability matrix is, and then find the transformation matrix T to get the CCFR. So we have already seen how to find the transformation T and to get the matrices AC and BC. I'm going to write those down directly. AC is, for this case, 0, 1, 0, 0, 0, 1, 1, 0, minus 1. And so if we have a similarity transformation T, then the eigenvalues A minus BK and AC minus BKC are equal. So we know that AC is TAT inverse and BC is T times B. So the special form of the matrices AC and BC would help us to find out the characteristic equation very easily. So let's see. We have AC minus BC times KC is 0, 1, 0, 0, 0, 1, and this is simply 1 minus, let's say, K1C, then minus K2C, and minus 1 minus K3C. Just this row and take the difference with the gain matrix Kc. So note that K and Kc are not equal and they are related by slope. The transformation matrix T. Alright. So now the desired characteristic polynomial is also very simple to calculate. This is simply and of Si minus Bc minus Bc, and it is simply SQ plus 1 plus K3C, so negative of this, times S plus S square plus S times negative of K2C negative of the first coefficient C minus 1 equals 0. Now we can compare the coefficients with the desired polynomial. So this is 30, K2C equals 325, K1C minus 1 equals 1250. So all of this implies that Kc is 1251, 325 and 29. Now you can find the gain matrix K. So this is simply Kc times T. Substitute the values of Kc and T and find out that this is minus 1251.7. is 0 minus 1, 2 by 3, 1, 0 minus 1 by 3, 0, 0, and 1 by 3. So you can compute this and find out the k for A minus bk. So now the second part is that we want to shift the eigenvalues, the real part of eigenvalues from minus 10 to minus 100. Okay, so then again we have the desired characteristic equation. In this case we have s minus 100, s plus 100, then s plus 100 plus 5i, s plus 100 minus 5i. So we can expand this, and this is simply s cube plus 300 s square plus 30025s plus 500. Okay, so we already have the gain matrix closed loop eigenvalue. So this is equal to 1 plus k3c. This should be equal to k2c, and this should be equal to k1c minus 1. So this implies that the gain matrix kc or k has increased. Or to shift the eigenvalues, loop poles to LHS, have to apply a larger input. So I hope that this question was clear to you. Now let's move on to the next one. So consider the LTI system. Short equals Ax plus Bu, where the matrices are diagonal matrix 1, 0, 0 minus 2, and B is 1b. Alright, so the first one is easy to derive the transfer function of the LTI system. Part B is to show that zero cancellation as a function which leads to loss of controllability. You already know how to compute the transfer function of an LTI system. This is simply g hat of s equals psi minus a inverse, and you have c and b. Assuming that d is 0. Okay, so you can assume that c right now is 1, 1. Write this down directly, you can compute what is Si minus A and then Si minus A inverse. So Si minus A is simply S minus 1, S plus 2, 0, 0, and inverse is simply the inverse of the diagonal entries, which is 1 upon S minus 1, 1 upon S plus 2. G hat of S is S times 1 plus B plus 2 minus B upon S minus 1 and S plus 2. This is part A. Now for B equals 0, let's see if there is a pole 0 cancellation. So G hat of S becomes S plus 2 upon S minus 1 S plus 2, which implies that there is a pole 0 cancellation. Now let's see how does this lead to loss of controllability of the system. So we already know the matrices A and B. So for B equals 0, we have to figure out what A and B is. So 0, 0 minus 2, 1, 0. This is 3, 1, 0. See that the two columns are exactly equal. Or the determinant of C is also 0, which implies that the pair AB is not controllable. So B equals 0. There is a pole 0 cancellation and the system is uncontrollable. Tells us how does the pole 0 cancellation affect controllability of the system. Alright. Now let's move on to the next question. So find the similarity transformation. Transforms the controllable canonical form. So A is 6, 4, 1. Then we have minus 5, minus 4, 0. We have 0, minus 3, minus 1. It's 1, 0, 0. Is in the controllable canonical form. Find the gain matrix K such that the eigenvalues Pk are located at minus 1, minus 1, minus 1. We want 3 repeated eigenvalues at minus 1. Okay. So the first step to find the similarity transformation is to form the controllability matrix. So this is BAB square B. I'm going to write this down directly. You can check this later. This is 100, x minus 50, 16 minus 10, 15. We've already done this question, so this determinant is non-zero, which implies that the pair AB is controllable. We can place the eigenvalues at the desired locations since the pair is controllable. And now we have to find out the similarity transformation T, which is C, CA, and C square. Please note that C is not the output matrix. Written Y equals CX. Alright. So in this case, C is going to be a row vector alpha 1, alpha 2, alpha 3. Already done this question. So alpha 1, this is 0, 0, and 1 by 50. We know what the transformation matrix T is. We know what T inverse is. And then we can find out AC. This is simply 0, 1, 0, 0, 0, 1, the chain of integrators. And then we have, let's see, this is minus 19. I think I wrote it 14 earlier. Minus 19, 6, and 1. And BC is in the standard form. So 0, 0, 1. And now we can just design the eigenvalues for the pair AC-BC. So the desired characteristic equation is for repeated eigenvalues at minus 1, we have s plus 1 cube equals 0, which is s cube plus 3s squared plus 3s plus 1 equals 0. And then we have the characteristic equation system, which is AC plus BC KC. Alright, so what we have to do, we have s cube minus of this coefficient, which is just s. So let's just name this. We have alpha 1, alpha 2, alpha 3. And in this case, the characteristic equation is simply alpha 3 plus K3C times S. Then we have minus of alpha 2 plus K2C times S. We have minus alpha 1, which is Z. So this is 1 plus K3C. This is 6 plus K2C. And this is just minus 19. D1 C. Minus 19 plus K1C. So now let's compare the coefficients. should be equal to, let's just write down, minus 3 should be, plus K3C should be minus 3, 6 plus K2C should be minus 3, and minus 19 plus K1C should be 1. This implies that Kc is, so we have d, then minus 9, so after Kc we can compute the original gain, which is Kc times t. This is 1 by 3. Yes. Have the transformation matrix, you can multiply this by Kc to get the original gain matrix K. Alright, let's look at the last question, which is on finding the feed forward gain. Okay, so let's see. We have a closed loop system transfer function. So closed loop system transfer function is g of s equals s minus 2 upon s square plus 11s plus 30. So for this system to approach 1, at the steady state, should be the feed forward gain. Forward gain is denoted by P, so this is P times s minus 2 upon s square plus 11s plus 30. This is the ratio y hat of s upon the difference. The final, or at the steady state, this is s tending to 0, s times y of s, which is simply s times 1 by s, because the system has to approach 1 at the steady state, times p minus 2 upon s square plus 11s plus 30. Get this should be equal to 1. So we have minus 2p upon 30 should be equal to 1, which implies that the feed forward gain should be minus 50. Alright, so I hope that this question was clear to you. This is this phi of t should be 1 at the steady state. Which implies that the reference should be 1. Tracking problem discussed in the lecture videos. Alright, so I hope that the questions were clear to you. And We looked at the controllable canonical form and how to find the transformation matrix T using the controllability matrix. And then we found out how to compute the gain matrix K. So using two formulas, which was the direct method by comparing the characteristic equations. Next one was to convert to the CCF form and then compare the characteristic equation. Characteristic equation all the coefficients. And then finally, we looked at the design of the feed-forward game for tracking. Alright, so let's end for today. We'll meet in the next week's tutorial session.